Good morning, everyone. I hope you good sleep and are prepared for the lecture 1+1 of the IMS Wald lectures. My partner, please go ahead. Thank you very much. Thanks a lot for all of you who managed to get out so early. It's not the usual time for the UK. So let me just start by giving you a very quick recap for what we said yesterday. Remember yesterday, I told you a whole story about these scaling limits for 1+1 separation models. And we talked mostly about two limits that you can get. The first one was Edwards-Wilkinson, which is also the stochastic heat equation with noise. And the second one was what's called the X point. And that is a much more complicated object that was only described quite recently. And I gave you some evidence which says that there's essentially just one crossover process between the two that's given by the solutions to the equation. And the support for that conjecture is that basically all of the models that are known to exhibit a crossover between the and actually many models for which this is only in the sense that one knows that in some regime for all of those models where we are able to identify the crossover to that conjecture, and there are quite a few classes of models now where these are actually theorems. So the example that I gave you yesterday was this directed new curvature for the one environment, which is this year. But there are many other examples of that type. So there's originally the first example, so they proved this for the asymmetric simplification process, and there are variants of more complicated controllers, and then well, they had to look at partial result, and then by Yara and Kubinelli, and there are results by Kubinelli and Markovsky also about stochastic conservation laws. The results of Jeremy Porcel and myself, other models of inverted conservation. So by now there's sort of a huge spectrum of results of this type, and in all the examples that we know, you get now, the work I want to talk about today, the starting point, is actually when came to Warwick as a postdoc a few years ago, and we wanted to, the idea was to provide some evidence for the fact that this ballistic acquisition model, which was the second model I showed you yesterday, breaking among the stack, that model is indicated, which is still not known. And so we wanted to come up with a one-parameter family of models, which includes one on one end, and on the other hand, something that Wilkinson class so this ballistic deposition model, you can write it as an evolution of the height function of this type. So H is the top of your pile of bricks. And then imagine that at some point T, you've got some clock outside X ray. And then what's the new value? Well, you have a brick that falls down, and either it just comes to rest on top of the existing brick. In that case, the new value is the old value plus 1. Or it sticks to one of the neighboring bricks, and then the new value is the same as the corresponding neighboring value. That's either H of X minus 1 or H of X plus 1. And what it does is the first thing it encounters when it comes from the top, and so it takes the maxes of the previous three values, right? So that's the way this evolves. And so what we thought is, well, you know, if you come from statistical mechanics, if you see a maximum or a minimum, you think of zero temperature. And so whenever you have a maximum, you think of it as zero temperature, there's always a finite temperature version that you can come up with. And so here the natural finite temperature version is to say, well, instead of just taking the max, I choose one of the three values at random, but I don't take them with the order, I take them with weight proportional to the value itself divided by temperature. So then, if the temperature is zero, I go very, very small, like basically just the largest one. If the temperature is infinite, and so clearly for temperature equal to zero, you just recover ballistic equilibrium. And so then what we thought as well, for the value infinity, this seems like some sort of a free object in the sense that it's something uniformly value without doing any sort of optimization or something. And so since, you know, in physics, that the free object in one dimension, this is a heat equation. This is a heat equation. So it turns out, well, okay, maybe actually, let me show you why it converges too. So here is, let me see. Okay, so this is actually what you get if you let this evolve. Just speed it up. Try for a couple months to prove it. At some point, I set it up, and I just wrote this piece of code. And then when you see this is all the stochastic. And so, you know, it's clear that, well, first, if there is a limit, it's not continuous. You see the dots here. The scaling is also clearly not the Brownian scale. So remember the yesterday the sort of I showed you the interface become pretty flat, and that was because of the square root scale. Here we just, as yesterday, we just zoom out so that breaks with the square. And you see it fluctuates. The fluctuations in this direction are about the same size as in this direction. Any difference? So, okay, so then the natural question here is, you know, what is that? Once you know that it's not the stochastic equation, you try to actually figure out what it is. You find it's very easy to actually figure out what, at least what's the K point. Points. It's actually very easy to figure out what the K point distribution is of that limit, because the discrete process has the following graphical construction. So what you do is you take, so again, horizontally is space, vertically is time, space is discrete, right? So then, like, each vertical line here is a time line that corresponds to one of the sites in space. And now you throw down, of course, some point process on each of these lines with the back measure, the intensity measure. And then for every event for some point process, you randomly either, and with equal probability, you either to the narrow to the left and narrow to the right, or a red cookie. And so then you have this picture, which is what I put on the screen here. And then if you want to figure out what the value is, you know, of that process at some given space-time point, which is some point on one of the lines, like this one, for example, all you have to do is to kind of go backwards in time and follow the arrows and count how many cookies when you follow the arrows. Okay? And so for example, the value here would just be the value of the initial conditions, they are time 0 at this point here, plus 2, because there are 2 cookies. away, whereas the value here would be the value at this point plus 1. There's only 1. Right? So if you sit down for 5 minutes, it's very easy to convince yourself that this graphical construction precisely gives you the process that I described to a slightly more formal way. And then obviously, once you have this graphical construction, it's clear what it rescales. Right? I mean, like all these three lines that go backwards in time, they're just continuous time on the walks. They obviously are just motions. They obviously coalesce, right? So two of these guys together. And then, the number of copies that you're moving on the way, well, there's going to be an average number, which is just, like a third times t. But then this, remember, that's a low number, this is just time. And then the fluctuations are there, just going to be. And it's going the way that central limit theorem works, right? So if you have k points, now what you do is draw k coalescing Brownian motions backwards. Now that gives you sort of a Florence, right? Because these guys coalesce, they take 0 at different locations, so you have a bunch of trees, maybe more than one. And then they are sort of, you have this tree structure, so you have different branches. So each branch has a certain length, the length is the starting time minus 48 time minus the starting time. And so each of these branches, you apply a random variable, a normal random variable, the value equal to the length of the branch. And then the value of the leaves is given by the sum of these normal random variables, sum over the branches that you have to traverse in order to go back to the root, and then you have the value of the initial condition of the root, right? So that picture is clearly this picture. And then if you think of, how does it scale? Well, clearly there's a sort of scaling, the space-time scaling is the Brownian, so that's bj for 2. And then the 1 comes from, essentially there are sort of 2 1/2 exponents, so to add up this Brownian motion on top of the Brownian motion. And if you sort of sit down for 5 minutes, again, you can figure out that the alpha exponent has to be 1. And that's what we saw in the simulation. So here is another model that would be one in the same universality class, which may be more sort of closer related to the sort of models that people interested in population theory are familiar with. Where you take your even lattice, then for every point of the even lattice, you have 2 possible outgoing arrows that point downwards. You pick one of them, but then you furthermore color all these arrows randomly, like I do. And then you can do exactly the same thing, right? So you can think, for example, you can say, well, the value at any one point of the given lattice would just be obtained by following the trajectory backwards, counting how many, say, blue arrows you traverse, and then adding this to the initial condition. So that's clearly just another discrete model which is exactly the same flavor. And same thing is even more or less trivial, but the k-point distribution. So the distribution of the sky converges to the previous slide. Now that tells you something about the k-point distribution. It's not that trivial to actually have like path information, right? But if you have a k-point distribution, right? I mean, k-point distribution can be very badly behaved in a pathway sense. You could just imagine, for example, on the real line, just sort of indeterminate more random variables at every point, and that's just one of the processes. So if you want to have some kind of more pathwise information, then what you would really want to do is you would want to understand the scaling limit of this kind of picture in a sort of strong enough topology so that things sort of provide that function function, the construction of this height function, provides in the limit that continues now in that topology. Okay, and that's more details about that are going to be Giuseppe's talk. I think it's afternoon or tomorrow. So if you want to do that, there's an object that shows up naturally, which is the Brownian web. So let me just show you a picture of the Brownian web. So that's the Brownian web. So the Brownian web is the thing that you get simultaneously a Brownian motion from every space-time point, and you make it correlates, right? So here you have a Brownian motion that starts from every point of the street, and well, so whenever two guys coalesce, the color here after coalescing is the color of the older one of the two. It does have a well-defined age. And so then that would give you some sort of color of the frame. You see the coalescing Brownian trajectories. And we start from every single. So that's an object that was introduced by Brownian Kaufman Vendor de Grano, so back in the late 90s. And so if you want the scaling limit of this guy, it's obtained by taking this Brownian web. Now viewing, so originally the Brownian web is considered to be what you do is you view this as a collection of trajectories. Then you sort of compactify to the natural way that sort of goes this picture. And then you view it as a sort of compact set of trajectories in compactification of R2. That's not a terribly useful point of view for our purpose, and we rather want to view this as a tree, so a real tree, set of an R3. So it's a sort of random, continuous R3 that blocks Alice's R3. And well, you can do that as a construction. Now, there's actually quite a nice story that you can tell, but I'm not going to go into details. But when you have this Brownian web, there's actually a dual Brownian web that goes with it, which is sometimes the trajectories that go forward in time, right? So here all the Brownian motions are going backward, downwards, and before that downwards. You can actually, what you can do, you can follow trajectories forward in time, weaving your way through these backward trajectories. And there's actually, from every single point in space-time, there's a unique way of going forward in time that allows you to not cross any of these backward trajectories. Right? It's sort of not obvious in the continuum. It's actually kind of obvious in the discrete case. Right? I mean, in the discrete case, here, clearly, we look at the centers of these squares. Well, just from the construction, you can see that upwards, there's always exactly one direction that you can go. And that really gives you a view of construction, which below is the same. The original construction, but just coming up instead of coming down. But it's obviously not independent, and it's the opposite of independent. You recover completely from the original guy, and it's a non-trivial fact that was already proven by Wald and Werner, but that property survives in the continuum, right? So the continuum guy, the dual one, is a measurable function, original guy. And so then you can actually link the Brownian web to the special points. So the Brownian web has a number of special points. In fact, there are exactly 7 types of special points. So the special points there's actually one of the 7 types is not special. So that's not this one, right? So the non-special points are the normal points in which there is one trajectory coming out backwards in time, and there's one trajectory of the dual guy going forward in time. So you do, if you want the trajectories of the dual guy, you can have the trajectories of the original guy. Now, of course, there's also points like that. If you're on a trajectory of the Brownian web, and not a special point, because it doesn't just have a trajectory coming out, it also has one coming in. so that would be a point like that. Then you would have points like this, where the two of them coalesce. And so then that's even more special. Where you have two trajectories coming in, one trajectory coming out. And it turns out that there are several other, right? So there's less obvious ones where there are points where you actually have two trajectories coming out, or even three. There's very few of those. So there are these kind of funny points where you have one trajectory that sort of just cancels with one other one. Anyway, so all of these points, you can sort of link them to the description of these guys. So, for example, it's not too difficult to convince yourself that the locations of these discontinuities here, they precisely correspond to points that are on the trajectories of the dual Brownian web. Right? Because if you're on the trajectory of the dual Brownian web, that kind of separation points, which you have two Brownian web, and that means that if it's a continuum limit of the value at that point is not to follow two trajectories. Then I told you there are even more special points in which you can actually follow. And that corresponds to what happens when two of these singularities collide. Clearly happens. I mean, you see on the picture sometimes even some of these towers disappear, right, because they're sort of very narrow and then the singularities collide. And by the way, so we call this process the Brownian process. Right. So there's a number of properties that we can prove. So, for example, we see that clearly the correct scaling space is the scaling of one. And so you can ask yourself, well, if you take a little increment and then you divide it by the length of that increment, that should be of order one. So what does this look like? Well, you can show that this converges to a Cauchy-Riemann variable. That's actually quite easy to show. The reason why it shows up as a Cauchy-Riemann variable is basically a Gaussian with variance given by an independent one-half stable Riemann variable. The one-half stable Riemann variable is like the hidden part, the hidden part of two Riemann motions. So it's quite natural how this shows up. In fact, if you take the stationary version of that process, and in the stationary case, the increments are exactly what's this thing stop working. So in the stationary case, this thing is exactly, increments are exactly Cauchy random variables. Now, that suggests, right, in the other two examples that we saw, practically the fixed point, for the stationary process at fixed time, is exactly a Brownian motion in space. So naturally, you can ask yourself, is this guy going to be a Cauchy process? Maybe a process with that scaling component. And this actually, the answer is no. And as a matter of fact, it's no in the sort of strong sense, in the sense that finite interval space. If you look at the law of the process on a finite interval space, and not more signal with respect to the law of the Cauchy process. Which is actually, I mean, it's not terribly difficult to prove. But you can still say some positive things. So, for example, you can prove that at fixed time, it has a version which is parallel, and it's like something value. Actually, it's not parallel with values in parallel processes. So, how to think about it is very difficult. You can't find, at least you weren't able to find any sort of topology on this convex path in which the convention of singularities becomes or even doesn't even have left limits. which is sort of a slightly weird property of these Cadillac topologies, and you can't see, it doesn't seem to be possible. So now if you take that process and you adjust, you change sort of the temperature, right? This was the infinite temperature version, 0 temperature was the next position. So you expect that there's a crossover regime, high temperature regime, between this point. And that's the sort of thing, well, you can sort of see, you can see this from the simulation. So if you somehow put yourself into a high temperature regime, so that would be like a, so here it's an inverse temperature. So it's very small inverse temperature. So for example, 0.03 or something. Then if you continue running that thing, you see that it immediately flattens out. And it looks much more like the simulation that I showed you last time, even though, of course, if you zoom in, sort of locally, it still looks a bit like the Brownian castle, right? So locally here, you still see these. It would be even more if I took a smaller value. But now, unfortunately, this will not be proof. You don't have any kind of proof that if you take the temperature high and stay down to the correct scale, there is a limit to what we do have, on the other hand, is we can characterize some crossover regime between this Brownian castle and the other free guy, which is the Wilkinson process. So that's the heat equation. And the way you do that, so what's the perturbation? So the perturbation is that in this backwards characteristic, right, so you have this Brownian web, and you follow these trajectories backwards in the Brownian web. Well, occasionally you're allowed to actually jump over to a different trajectory in the Brownian web, but only with somehow very small force. And then the theorem we have there is that, well, so then that's those joint with GF and wrong next soon. Let's not get it here. But if you scale things correctly, you can get a limit, and the limit actually still depends on a measure, and I'm going to show you the measure shows up. And it genuinely depends on it, right? So the situation here seems to be very different from the situation that we have between Wilkinson and the right? So remember, in that case, we have this huge evidence that there's basically only one crossover. Exactly one guy, which is the equation, which looks like KPZ at large scale. Here, we have a whole family that depends on the measure on the interval 0, 1. So it's an infinite dimensional family. And we can prove that they're all distinct. So they're all genuinely different processes. And they all cross natural sort of crossover processes between the Brownian castle and this stochastic heat equation. Okay, so the situation is really quite different here. And so here is how you get them. So you take the same graphical representation as before with for that second model here. And now you take so you mark some of the points, right? So you take a small fraction of them. So that's your small parameter epsilon. So you take a small fraction epsilon of your points randomly. And those guys, you mark them with some value. Right? There's a different value for every point. So P1, P2, P3. And those values P themselves randomly according to some measure on the interval 0, 1. Right? So that's the measure you do. Okay, so that's some measure you on the interval 0, 1. You draw these points, these values P according to that measure in an IID way. And so now that's your randomness that kind of drives the process. And now the way you construct the process is you still follow trajectories backwards. So now I can't point Also, you follow trajectories backwards, but then when you reach one of these points, some of the mass goes left and some of the mass goes right. So here you have sort of P that goes left and 1 minus P that goes right. And so the value up there is equal to P2 times the value of the purple point plus 4, because there are 4 blue guys that we follow that way, plus 1 minus P2 times the value of the green point plus 5, because there's on that trajectory there's 5 blue edges that it covers. So clearly you see that if the intensity of these guys goes to 0, then you're just back to the Brownian castle. And well, if the intensity of these guys is over 1, then it turns out you can prove that the process you get in that way actually just converges to the stochastic heat equation when you rescale it. And so if you make the intensity small, well, then if you scale out of the correct scale, you converge to something non-trivial, which is somewhere in between. And then, of course, you can take that guy in between the two crossover processes. You can give an intrinsic construction. And so it's sort of related also to this work by Lejean and Raymond from IMS, also these coalescent flows of Brownian motions. So you can sort of clearly see, right, that it's sort of related to coalescing and then breaking up again. And so in particular, that measure nu also has the same interpretation as it has in these coalescence. In particular, you can define that process also in cases where the measure nu is not a finite measure. It's an infinite measure as long as it actually integrates p times 1 minus p. Okay, it's kind of clear in sort of on the previous picture. If the p's are very close to 1 or very close to 0, then it means that at those points it's still almost deterministic, and therefore you can have many more of those p's. Right? You can have sort of a higher fraction of those p's, and you would still converge to something which wouldn't just be the one with the high density of over 1 p's. So you can actually, that measure nu can be sigma finite rather than just finite, as long as it integrates the function p times 1 minus p. That's exactly the thing, that the condition that shows up with the study before that. And so in the sort of theorems that we have, so we can show that you have an intrinsic construction of this crossover process. You can show that it really converges to the Brownian castle at small scales to advance circuits on large scales. Interestingly, in the case where the measure nu is finite, you can show that that crossover process also has jumps. We don't know whether it has jumps or not. If the measure nu is infinite, it's not clear, and it's not obvious from the simulation we done. Interestingly, when the measure is finite, it seems the convergence to the Brownian castle at small scales is actually locally uniform. There's a natural way of coupling that. That coupling is locally uniform, which again is not obvious because the limiting guy is discontinuous, right? So usually we don't converge uniformly to something. Here you do. And the convergence to stochastic heat equation at large scale, that one we believe that it's actually locally uniform, but we weren't able to prove that. We're only able to prove that it's locally uniform after you smooth that out on mesoscopic scale. And you can do the science of how big the mesoscopic scale has to be. Right. So let me just show you what this guy looks like. So to reset this. Okay, so if I take the Okay, so here I have the Brownian castle, so that here the epsilon is sort of 0 if you want. And so then if I increase epsilon, so say 0.01, which is still quite small. So what you should see, so here, this is a simulation of this crossover process. In the case where that measure nu, the delta measure of a half. Okay? So that means that all these p values, you actually don't really draw them randomly, they're always a half. Okay? And what this means is that sometimes this discontinuity is split. We actually split in the middle. That's actually what you see. It goes sort of somewhat fast, but sometimes when you see you have sort of rather tall discontinuity, sometimes you see a little sort of a very small guy that sort of tries to come in at about half the height, and sometimes it breaks it. Okay, and so the fact that they come in at half the height, that's because delta measure half. So that's good for you a half delta measure a third and a half or 2/3, then they would come in at either a third of the height or 2/3 of the height. So that's the interpretation here. And so you see, if I take the epsilon a bit larger, say 0.05 or something like this, then you see immediately this thing gets pretty much involved. And so you already see that here it kind of tries to become continuous. So here now what you see is that some of the macroscopic shape is trying to follow the heat equation. So essentially what you run out, and then you have fluctuations in fall. And the fluctuations in fall also has okay. And so just for the last couple of minutes, there's some work that we have in progress at the moment, which is in the Tommaso Rosati. And so that's kind of interesting. You can ask yourself, can you obtain these kind of crossover processes from some stochastic PD? Obviously, I would ask myself that question. And so here is a natural sort of stochastic PD model that one might think falls into that class. So what you do is you take two independent stationary function value linear processes. So it's a linear process, but it's not linear process in the linear process in some other space of functions. And it's stationary in the sense that it's functions and you translate them in space. And the covariance is smooth and conductor support, right? So basically, you take the process, look at it at fixed time, you see a state of reduction process. And at every point, you just follow the Brownian motion in time, but they're correlated in such a way that fixed time is something smooth, and Darcy, but with the conductor support. One apart, you just see the motions. If you take two guys like that, W and WR, they don't need to have the same covariance. It's just features. That's the one just to normalize. And then what you do is you look at this kind of equation, which is so you have a right. So you want to get Edwards Wilkinson some regime. So you want to see some sort of heat equation. So you take the heat equation around in front, and of course the fact that I put epsilon square rather than epsilon is again just conventional, so the scaling goes max afterwards. And then you have two extra terms, so there's an additive noise term, and then there's some kind of random transport term. And the random transport term that really corresponds to following these kind of backwards characteristics that are given by the Brownian wave, right? So in some sense, this term here corresponds to following the Brownian wave kind of backwards in time. This term here corresponds to the projects that are collecting along the way that gives some Gaussian fluctuations on top. And then this is some perturbation of that, which will correspond to somehow this possibility of coming over from one characteristic to another. So the conjecture that we have is that if you take that guy and you scale it with the correct scaling, right? So that's this one. kind of scaling, which is the scaling variance of the Brownian puzzle, then this should converge to a new Brownian puzzle, and it should be one where the measure nu is infinite. And it's a very specific one, actually. So if you take measure on the real line, then you take the error function, you take the cumulative distribution function of a normal distribution, and you push the base measure forward onto the interval 0, 1 by that variable, right? So then that gives you a sigma finite measure on the interval 0, 1, only non-integrable because it has some singularities of 0 and 1, but they are actually overline singularities, so it's the impact one. It actually integrates the alpha transform. So the conjecture is that it converges to that guy, and so there's two interesting things here, right? So the first one is that this measure here is always the same. Right, so it's independent of the covariances of W bar. We believe that that's somehow a consequence of the fact that these guys are white noises in time. So if we take, right, you would expect a similar result when we have much less evidence for that. But you'd expect a similar result if you replace these guys by just some space-time stationary smooth random fields. So then there's no component, this is the coefficient normal product, which is functions. You would still expect the same kind of result, but in that case, the nu would probably depend on the kind of space-time covariances of these guys. Okay. The other thing which is interesting is that if you rescale this, right? So you take that rescaling, divide the equation for the rescale guy. Formally, every single term on the right-hand side actually goes to 0. Kind of a weird thing, but it still converges to a non-trivial guy. So, right, because we do a parabolic rescaling in space, so that coefficient epsilon square remains an epsilon square, right? So it's not that the reason that we get to that scaling is because that epsilon square is equal to 1. If that epsilon square stays an epsilon square, whichever way you scale that guy, it's always an epsilon square. And the way the noises are rescaled is equal to, like these W epsilons, they are the ones that you would obtain if you rescale such that you get space-time noise. So they would be approximations to space-time noise, but then they take out an extra square of epsilon out in front. So in some distributional sense, that guy goes to 0. And that guy, well, formally, it also looks like 0. Right, so the reason why you would still get sort of the Laplacian that comes out for the stochastic heat equation that you get as the large scale behavior of that guy, it's not that Laplacian. It's really a Laplacian that's kind of generated. So, okay, I think thank you very much. Are there questions or remarks? Good question, right? Yeah. Yeah, that's correct. No, I mean, it's still good. So we have a pretty good description of what the guy looks like at fixed times as a function of space. I mean, we have some description of the space-time process in the sense that you have that link between the behavior of singularities and the dual Brownian one. That's something that sort of tracks things in time. We also have some, so in the for that crossover process, So you can actually, like this intuition saying that discontinuity is kind of split at the location that depends on that measure, that you can make it sort of precise, but in the sense that you can, take that value, you can start with an initial condition, and for a short amount of time. And then what you see is that, well, with high probability, you just see a step function with the same height, but then the next order, you would see something which has exactly one other step in the middle. Kind of formulate the Well, I think Martin.